Good morning, everybody, and welcome to Physical Science 1. This is basically an introductory course to physics. One of you guys asked about the lab. There will be no lab in this class. However, at some point you will be doing things at home, okay? You will be doing observations. You will be doing stuff related to that. One of them, I already mentioned it, is what's playing behind me, and that is the Mars landing this Thursday. Okay, this Thursday we still have a session, okay, in the morning, but we will have it shortened though, because there will be an assignment related to the Mars landing. The thing with physical science one is, we will learn everything, okay? We'll start from the basic concepts of motion in physics. We'll discover the laws of physics. We go into thermodynamics. We go into electricity and magnetism. And then after that, we get into the structure of the atoms, basically to explain the properties of solids and rigid bodies and things like that. And then we get into how this atoms basically interact with one another. We get into chemistry. As a matter of fact, we get into organic chemistry. And then later on, properties of rocks, which is an extension of, again, of what we learned in motion, in addition to what we learned in chemistry, which is going to be a branch of geology that we're going to get into it. Basically, that's the other part that we'll be discovering in here. Finally, we end this thing by studying the solar system, which includes what's happening this Thursday. The planets, the inner planets, Mars, Venus, Earth, what is it, the other one? Mercury, okay, and then the outer planets, okay, the gas giant, Jupiter, Uranus, Neptune, and I must have missed something. Neptune, Uranus, Jupiter, and Saturn. The big deal, okay, with the rings and so on and so forth. Okay, so those are the basically the things we study, and then after that we go even into the galaxy and the entire universe. This class has everything. Okay, you're gonna learn everything. Okay, now, I mean the downside to that is that we're not going to delve into a lot of detail on everything, but hopefully we cover a lot of stuff. So like I said before, it's unfortunate that this landing happens in the beginning of the semester. I wish it would have happened at the end of the semester, but we really don't have control over that, as we will see later on when we get into astronomy, that there is a window for the landing that, that corresponds to the motion of the Earth and Mars. And when they are the closest from one another is when this happens. So that's basically why it happens now. Anyway, so that's basically the stuff in this class. Do you guys have any question for me? I know one of you already asked about the lab, and I answered that in the sense there will be no lab. However, I will be doing demos. I have 2 cameras in here. I will switch cameras in here to do some demos at times. And also you guys will be doing observations at home. Any other question before we get started? Okay, before we do that, we still have stuff to talk about in terms of business. Okay. You have, of course, the entire course is online. It's on Canvas. That is where you're expected to go every day. The main page or the main link when you go to Canvas is actually going to be on modules. So that's where you're supposed to be going on a regular basis. That's where you see most of the things that are happening in there, namely the assignments in there, namely also the notes that I post in there, and whatever is there. So basically, I will be posting for you guys the PowerPoints, okay, and along with discussion items, okay, and I will discuss exactly what those means, okay. And of course, there will be homework assignments in there, and there will be also quizzes in there, and there will be tests in there. So that's basically what you're supposed to be doing on a regular basis, day in, day out. You're supposed to be in that page. However, when you come home to the Canvas, it's going to be the syllabus of the course. That gives you an overview, basically, of what we're doing in this class and the rules and so on and so forth. One of the things I want you to have to pay attention to is the schedule for this class. There is already a change that I'm going to make to the schedule, and it says tentative schedule. because it's going to be tentative. One of the things I'm going to change is the exam 2. It's scheduled right now on week 8. It's going to be bumped to week 10. Okay. So that's a change already that I'm hoping that you guys have a note of it. I'm going to send a message to make sure that everybody gets it. And exam 2 was on week 10 because of the fact that week 10 is going to be an on-campus testing for my other classes. I teach 5 classes. I have 3 of them that are required to be on campus for the midterm exams. You guys are not required, so you're going to still have your exams online. But because I cannot be physically online at the same time on campus, so that's why I'm moving that exam to week 10. Not week 9, by the way, is spring break. So it's immediately after spring break, just not before it. So that's a change that you guys are going to have in that in the schedule right now. Okay. So again, please pay attention to all of these details in terms of the final is on June 8th. I expect the grades to be ready by June 9th. So the final grades should be ready by that day. Okay. If I make a mistake, and sometimes I do, please let me know immediately that there is an error in my grade or there is something that I did not include or something like that, so that it does not go beyond, because the graduation is actually June 11th. So we don't want to be going back to the college and asking for requests for special papers and stuff like that to have corrections and things like this. It's doable, but I'm hoping to do it before the that due date, okay? Okay, there is an assignment already for you guys. I hope that you guys have had a look at it. Any questions about the syllabus? Anybody? Okay. Let me go into the models then. There is, first of all, please read the community rules on how to communicate with each other, because we are really online right now and we have to have some sort of established rules, and that's what that is. Then there is an assignment, okay? You're supposed to read the prompt. You're supposed to have an initial reply by due date, and you're supposed to have a second reply or a first post by the due date, the first due date, and then two replies by the second due date, okay? That is basically a requirement from your the discussions are locked. What do you mean? In corner, are you asking about the discussions right now on the models? Yes or no?
Yeah, I couldn't find them. It just says they're locked until a later time.
Yeah, that's the thing with them, is sometimes you see something and it's when the due date for it comes in is when they are available. Okay. I'm going to come to those discussions, but right now this one should not be. The diversity and Nobel Prize, that should not be an issue. You have access to that. Can at least one person confirm that they can see that?
No, we do not. I do not.
What? Let me check on it then. Why is it February 22nd? I don't know what happened in here. I'm sorry about that. Okay, I must have been, look, I have had my second shot yesterday, okay? So if you don't see things consistent with me, that's because of yesterday. Okay, can you check on it, please, again? Okay, at least I see some heads nodding. Okay, I need somebody else at least to confirm that they are looking at it good. Yes? Corin, since you raised, okay, good, good. So we have quite a few people now who,
Yes, it's
okay,
good.
very good. Okay, so the idea here is, let me see if I can share the screen in here. Can I? Hold on. Share. Screen 2. No, I want to share this assignment only. I don't want to share the entire screen. Can you guys see it?
Yes.
Okay, very good. So basically, the assignment in here has two due dates, two important dates. One is this Saturday, and the second one is actually Tuesday, a week from today. Okay. So what you're supposed to do in here, again, is you're supposed to go and research and find people who have contributed to science. Please stick to physical science, either physics, chemistry, or geology, if you like, and astronomy. I mean, you might be tempted to find somebody in biology, but I don't know. If you find them and that's the only person, or you find her and that's the only person, that's fine, okay? But try to stick to physical sciences. And because that's really where the problem is right now in terms of diversity in these fields. And then basically follow the prompts in here. Include a picture of yourself and include a way for me to address you, okay? Because sometimes it may be obvious to you, but a friend of yours probably would use the wrong pronoun. So please use that too, that this is how I'd like to be addressed. And respond to this prompt, please, as soon as you can. Let's do this this Saturday, okay? And then the second one is in there. As a general rule for this one's in here, you will, let me change the view in here and look at it as if I am a student. So this is how you guys would look at it if I'm one of you guys, okay? You're gonna come in here and show rubric. That's going to show you exactly how it's graded. And it tells you what needs to be done for you to get the full mark in here, okay? That's typical of all of my assignments. You should see rubrics, you should see grading guidelines, so that actually if I don't grade your stuff, if something happens to me tomorrow, somebody else can come and grade your things. Actually, you can grade it yourself if you want to, okay? Any question about this assignment? No? Okay, very good. So what else in here? Let me go back into the models to see what's going on. Okay, again, you have the lecture notes and you have the terminology, the key concepts that you really need to focus on, and then the discussion. Okay, this one probably is still locked. Okay, and the reason for it that it should be locked, let me see exactly when it's supposed to be available. 8 p.m. today. And let me tell you why that is, okay? Let me go back into the models again, leave the page, I don't want to edit it. And let me show you how it looks like so that you guys have at least a feel for it. Okay, let me stop sharing the screen now and share with you this page. Okay, at least one person confirms that they are looking at what I'm looking at, which is chapter 1 discussion, and then says below you will find the recording for today's lecture and so on and so forth. Yes, no?
Yes.
I need, okay, very good. So basically what this will contain is exactly the recording of today. Right now it's a blank page, okay? So right now it's actually, if I try to play it, nothing is gonna play because we did not finish the session. So once it's finished, I'm going to upload the link from my YouTube account here, and then you guys can go because some of you are not going to be here. Some of you, for one reason or the other, probably are not being able to attend the live session. So what happened then is that they're supposed to come in here, look at the entire video, and pick up 1 or 2 items of the discussion today. You guys understand? It could be a question from the lecture. It could be a question about the process and how to do things. It could be a question related to what you have to do at home to finish the assignment. It could be anything that is related to the topic of the day. So let me stop sharing in here. So basically, as we are doing the live session, like right now, there will be something that pops up that you're supposed to be doing, okay? And in there, you're going to come up and answer the prompt, okay? Answer the discussion and say today's discussion point or points up to technically 5 points. Usually I try to make it less than 3, okay? There could be 1, there could be 2, there could be 3, there could be 4, there could be 5 items that you need to pick up from the discussion of that day, okay? That tells me that you actually have either attended the live session or actually watch the live session, the session that was recorded afterwards. In other words, you're doing your work, you're participating in the class. Now, somebody might think, okay, I really don't have time for this. So what I'm going to do, I'm going to come in here, look at what other people have posted, and I'm going to just copy their stuff. That is not going to work because you're not going to see anybody's comments until you actually enter your first. You guys understand? So if you don't enter your first post, you're not going to see what other people have been talking about, number one. Number two, if you do change your post, let's say, for example, you edit it, you don't like it because you just put something in there just to see what everybody else is saying. If you do that, if you edit it, it's going to nullify it. It's going to cancel it. So while we're doing the live session, have notes, please, taking what we're doing, okay? If a question pops up, we'll discuss the answer for it, put the answer in there. Do not immediately post the replies in there because there might be another one coming down the road. So wait again for the second prompt to come in and the discussion points, write them down. And then when we're done with the live session, you go and post your comments. Do you guys understand that? If you're watching it recorded, the same thing. You take your notes, you put the note in there, comes the second point, you make in there, the third point, if there is a third point, you make in there, and then you're ready, you're done with it, you come back again and you post your notes. So whether you attend live or you attend recorded, you have fulfilled the requirement for the participation in this class by doing this assignment. I'm not going to be at the end summarizing the questions, okay? I would try to refrain from that because then somebody might skip toward the end and just see the questions of the day and cheat his or her way out of this. So no, okay. During the discussion, I will be more than happy to answer it and then we continue. So this is the first question of the day, okay? Today, how to participate is by watching the entire video or attend live, taking notes and answering the prompts in there, okay? So that's what I want to see there today, okay? Is this clear? Okay, I have 1, 2, at least the people I see, 3, 1 nodding heads, and I have a thumbs up from somebody. Okay, very good. So I hope that everybody, okay, I have a lot of people now. Okay, very good. So now I hope that you guys understand. So today's discussion, item number 1 is basically the fact that how to participate in the class, how you're going to ensure you're going to secure your participation grades. If you'd like to skip participation grades and go straight to homework and quizzes and things like that, that's fine with me, but you're going to be basically missing 10% of your grade. Okay, you're going to be operating out of 90 out of 100, and that's not going to be good. Okay, so I don't recommend that. Okay, Gretel, did I say it right? Did I say it right, Gretel?
It's Gretel.
Gretel, I'm sorry. Okay, listen. Basically, today's item is how to participate in the discussions for these chapters. So that's the question. Okay, the answer to it is by either attending live or watching the entire video, pick up the questions from there and the answers to them. Do not answer immediately until the video is completed or the session is over. Then you know how many questions and their answers and you post them in there. How you're going to put it in your own words, okay? That's the way I put it. So you're going to put it in your own language. I need to see a confirmation from you. Does this make sense to you?
Yes, thank you.
Okay, very good. Anyway, so that's basically in terms of business, okay? And we will see this more in practice and things like that. Honestly, the first one, usually there is a big kind of a grace period on it. So because I really want you guys to get the hang of it, because I want you to really be participating in this class, okay? But try to be punctual with it. If you guys don't have any questions, now we need to jump into the business in hand, which is physical science. No? Okay. So let me get into this class in here. Okay, I must also have, okay. For some reason, it removes it from that screen in there. I'm supposed to have two screens anyway. Can I try something else, guys? Hold on, okay? I'm gonna try something, okay? Stop sharing again, let me share again, but this time screen 2, it's still the same thing. It's giving me the entire screen. Sorry. I don't want by accident to display some stuff that's probably not. Okay. Anyway, so this is the chapter 1. You should see the notes in there, okay? You should see it under basically outline, course chapter 1. And basically it's going to talk about the patterns of motion. We were captivated and always basically fascinated by it ever since we basically started to notice and discuss motions and things like that. So this is one thing that dates to a long time. People started to quantify it and basically come up with an explanation for it. So Mr. Aristotle came up with a notion that the natural state of object is rest, okay? They don't want to go anywhere. If you move them, they will stop. That's basically what he said. Then Galileo challenged this idea, actually, 2,000 years later almost, challenged this idea, and he came up with the idea that the tendency of objects is actually to be in motion, not to be stationary, okay? The fact that an object is stationary is just preferential place for you to look at it, that's all. So, and then we're going to discover the concepts of basically mass, which is really the concept of inertia, which is a big deal from today's chapter, by the way. Inertia is a very important concept that you really need to have an understanding of it. This is one of the things that you're going to pick from this class. So when you're talking and you're asked, for example, what did you learn from this class? What is one of the things that stands out is the concept of inertia, which is really the resistance of an object to the change of its motion. If an object was at rest, it wants to stay at rest. If an object was moving, it wants to keep moving, okay? So that's really what the inertia is, okay? It's the resistance to the change in motion. Then we're gonna understand the concept of net forces, the concept of equilibrium. We have to develop a concept of a force, though. We're gonna have a simplified version of it to begin with. And as we move along, we're going to discover different kinds of other forces that are not included in here, okay? Then the concept of equilibrium, where in the world is an object supposed not to move at all, stationary, okay? And then the force of support, or the so-called the normal force, okay? And then we're going to discuss the dynamic equilibrium, basically, and that is equilibrium in motion, basically, when the velocity is actually constant. That is actually also equilibrium, okay? Case in point, when you're driving your car or sitting next to somebody who's driving the car, you could have a cup of coffee, full to the brim with coffee, and if the car is moving at constant speed, namely cruising with the cruise control, nothing will spill, okay? As if you're sitting next to, on your coffee table, for example, drinking your coffee. It's the same thing. So that is basically what that idea is. Then we're going to discover the concept of the force of friction. And speed and velocity, they're slightly different from one another. One of them is actually a number, namely the speed. So if you tell me, okay, I am on highway 91 and I'm doing 50 miles per hour. You guys are in Riverside. No, you guys are actually in Corona, okay? How long do you think I will be there? I'm 50 miles away from you. So you could do the math, can't you? 50 miles, you are doing 50 miles per hour, it's about an hour, okay? But you cannot tell me which direction I am at, okay? Are you coming from the Orange County side or coming from the Riverside side, unless I tell you which direction I'm traveling? And that is the concept of velocity, okay? That is a different thing, Okay? The concept of velocity encompasses in it the concept of speed. So the speed is just a property of velocity. There are two properties. It has a value, which is speed, and it has a direction, which is the velocity. Where are you going? Okay, that is basically what the concept of velocity is. It is what is known as a vector, okay, which is a mathematical concept to describe exactly what we're talking about, namely, a vector has two things in it. It has a magnitude and direction, okay? And then we're going to discover the concept of acceleration, because it turns out the velocity is the rate of change of position. If I tell you I'm doing 50 miles per hour, you expect my place not to stay in the same place. You expect me to change places at the rate of 50 miles per hour. You guys understand that? Every hour, I would have changed my location by 50 miles. That's what 50 miles per hour means. So if I am driving for 3 hours at 50 miles per hour, I would have covered a distance of 50 times 3, which is 150 miles, okay? So that's a rate. So the velocity is actually a rate, okay? Like, for example, if you're consuming, and you're lucky enough to have a Prius, 60 miles per gallon, then you know how much basically you have you spent on this car, on that trip, okay? Same thing in here. So that's a rate, okay? Ratio of two things, distance over time. The same thing with the acceleration is the rate of velocity over time. How much is changing in velocity with time? So it's going to be in distances per time per time. So that's basically the concept that we're going to be discovering in this chapter, okay? You guys understood all of these things, then we're done. We can go home now. Or actually, we are home, right? Sorry. Okay, so let me switch cameras in here. Let me stop sharing in here with you guys. Switch camera. And before man, let me remove the virtual background in here. Okay, so what you're looking at are two objects in here. So Mr. Aristotle said that these two objects, can I move the camera slightly? Yeah. They're stationary, okay? That's the nature of objects. They stay in their place unless you change them, unless you push them. So if I push this one in here, it has moved, didn't it? Yes? Okay, so now if I push this object with the same force, it has moved, but one of them moved more than the other. So why in the world is that? You guys see that? I have a golf ball that I found a long time ago when I was playing soccer. I don't remember even where. Okay. If I push this one, let's try to move it. Moved. If I push this one, actually it moves back and forth because the table is in kind of a, the desk is. So if I move this one, it moved, but not as much. So Mr. Aristotle argued that the nature of object is to stay in their places. They don't want to move. They want to stay where they are, okay? Unless, of course, you come and change them. Does this make sense? Somebody is suggesting their shape. Okay, here is the trick. I'm going to try to come up with a different shape. Oh man, it's horrible. I don't have, let me see. That's a very good point, by the way. Bear with me, okay? I have found another thing here. Okay, they're the same shape and the same size. And if I apply the same force, which one do you think will move further? Which one do you think will move further? The pink one, okay? So it's not the shape then. Okay, so it's the lighter, then it's a mass or the weight, okay? As a matter of fact, if somebody argued the weight, I'm going to think of this one, and I have actually another one I couldn't find it, that have a similar mass. They weigh the same, but one of them, this is actually copper. Another one is made out of aluminum. They weigh the same, okay? But with different shapes. So, okay, let me tell you a secret, okay? It's none of the above. It's not the shape. It's not the mass. It's not basically all of these things, okay? It has to do with item number one before the last two, the friction, okay? That's really what all there is to it in this thing in here. Okay, so let me switch cameras again. But I have a, okay, and let me put that nice video playing behind me again. Okay, so it really is the friction that plays a major role in here, not anything else, okay? You can try it. As a matter of fact, that's the whole argument that Mr. Galileo has made in that, let me go back into the sharing of the screen, is that this force is the one that causes problems for us, okay? It's the force of friction. So he was able to do an experiment with inclines, okay? And as he smoothed the incline further and further for the same object, the object can go further and further. So that's basically how the idea of this that it was challenged by Mr. Galileo, okay? So Mr. Aristotle basically, there are two kinds of motion that is straight up and down, or straight, and then there is violent motion. So he came up with all kinds of theories about it, and that idea held for a long time, for about 2,000 years. That's a long time, okay? People believed that that was really how things were. Of course, Mr. Galileo came up with this experiment, actually. So what he did, he took marbles and he dropped them on an incline, and he noted that if he drops them from the same point, that they would come in here and they would always fall somewhere in here, okay? They will stop at some point. So it seems like up front that Mr. Aristotle was correct. However, if he smoothed the surface, so he made the surface smoother, he noted that these marbles will travel further and further distances, okay? If he made it even smoother than this first time around, it's going to go further away. So he hypothesized the following. He said that, look, if the surface is as smooth as it can get, is the smoothest, basically that this object, there is no reason for it to stop at all. And the only reason why it was stopping or slowing down to begin with was because of a force, in this case, friction. So an object will keep its state of motion, okay? Like this marble in here, if I keep it and put it in here, it's going to stay there. But if I push it, it's going to start moving. There is no reason for it to stop at all. And that is really the concept of inertia, how it emerged from this whole thing. So the whole idea in here is this property of inertia, okay? Obviously, in the absence of forces, we expect the object not to stop. I mean, imagine the time of Mr. Galileo. Mr. Galileo lived around the 1600s, okay? He was born in the 1500s, something toward the end of the 16th century, and died around 1640 or something like that. There was no internet, no videos, no basically people going onto the interplanetary space, for example. For us right now with NASA and all of these things, we can see this thing. There is no problem with it. We have a lot of access to these things. But for his day and time, objects are stationary. You put something somewhere, it's never going anywhere, okay? Unless, of course, you put your phone or your Apple Watch, for example, in downtown Riverside and come after 3 days. Do you think you're going to find it in its place? So why is that? Is that a violation of Galileo's law that objects all of a sudden move on their own? Who's the culprit then? Can we do this experiment? Can you guys tomorrow go to downtown Riverside and put your phones somewhere on the street? Why not? We want to check this law to see if it works or not. No? No volunteers? Oh, guys. Oh, okay. Danielle came up with an answer. Okay. So maybe that's true. Okay. So don't try it. Okay. Don't blame me if you lose something in there. Okay. Anyway. So this is true, at least in the concept of physics, that objects will stay in motion or will stay in place unless they are moved. And that is because of the property of inertia. Okay. So this is the concept. Mr. Galileo basically also demonstrated that the reason why these two balls arrive in the same location at the same time, they don't arrive in the same location, again, is because of another force of friction, in this case of the air resistance. Okay. So again, all of this work led to the discovery of a, in the absence of friction, no force is necessary to keep the horizontal object from moving completely horizontally, okay? Now, in the case of an actual experiment, if you do it this way, there is a problem because it's going to be a projectile because it's going to fall this way because there is another force at play, which is the force of gravity. How are we doing on time? Good. Now, again, if there is no friction, the ball, as it bounces up and down, it's going to have the same height, regardless of this angle, even if it's smaller angle. And if you put it this way, it's going to go forever and ever and ever trying to reach that same height. So it's not going to reach it. So it's going to basically continue for this one. So the key concept in here is that the tendency of a moving object to keep moving is natural. Every material object resists change in its state of motion. This property of things to resist change in motion is called inertia. It's not the resistance to motion. You have to be clear on that, okay? It's a resistance to the change. So the key word in here is change, okay? I don't want the, what is this thing in here? Do we have anything in here to say? Yeah, maybe this one. So this is the key word. Change, okay? Change in motion. And that you feel it, for example, if you're sitting in a car, driving at cruise control, for example, going with 50 miles per hour, and then all of a sudden you hit the brakes. Then your body doesn't want to stop. It wants to keep on going in the forward direction. That is because of inertia. And that's why we wear seat belts, because we want us to be prevented from moving forward. Do you guys understand? The inertia is the one that keeps you going in the same direction. And the same thing happens actually when you go on a curve, okay? When you're turning, you feel, if I'm turning this way, I feel my body moving this way. If I'm turning in the opposite direction, my body moves in the opposite direction. It's the same culprit, which is inertia in this case. Because here is the deal. As you're moving this way and you're trying to turn, your body, your motion is changed. The direction of the motion is changed. And your body, your inertia wants to keep that direction. So it really is a property that has to do with the change in motion. Now, as long as you're going at 50 miles per hour, there is no problem whatsoever with it, okay? You don't feel anything. As a matter of fact, like I said before, if you have your cup of coffee full of coffee, nothing is going to spill as long as there are no bumps in the way, because up and down, that's actually another forces that come into play. And the water tend to resist the change in motion. And, or not the water, coffee, I'm sorry. And the road is smooth and there are no turns. Everything is 50 miles per hour. So you can have your copy and no problem whatsoever with it. So we got that one in here. So here is a question for you guys. The use of inclined planes for Galileo's experiment helped him to do what? What did he discover with it? What's the big deal we've been talking about in here? So you guys, when you put chat in here, C, yes, very good. Yeah, it has to be the inertia. I mean, that's the big deal in here, okay? So we're talking about inertia. That's what he discovered, okay? Here is another thing that is really not obvious, at least up front, but it is there, okay? This one was one of the mysteries that was there, but we couldn't really. The amount of inertia possessed by an object depends on the amount of matter, the amount of material that composes its mass. The key concepts in here of mass as being the resistance to the change in motion, and also mass as being the quantity of matter, that was one of the things that really puzzled scientists. Now we know, I mean, we knew that they were the same quantity. If you have 10 kilograms of mass, you really have 10 kilograms of inertia also, okay? But there is no justification for it to begin with until Mr. Einstein came in and basically in his general theory of relativity came up with an explanation for why the inertial mass, the gravitational mass are the same, okay? But we know that they are, okay? If you have a 10 kilogram, so if you weigh, for example, 70 kilograms, not you weigh, I'm sorry, if your mass is 70 kilograms, that's your inertia, whether you are in gravity, you stand on scales, or whether you're in a car trying to decelerate or accelerate. Again, it takes a lot of force now to move a large object in here versus a smaller object in here, okay? Of course, it depends on the friction also, because you will have less friction to move with. So twice the mass, twice the weight. And that is what we observed on Earth, okay? So if you have a 70 kilograms and you double the 70 kilograms, it's going to weigh more. That's basically on the scales, okay? So mass actually, which is the, again, we defined it as the inertia, which is a property of the object to resist the change in motion, has to do also with the amount of matter that is in the object, okay? The volume is the space it occupies, okay? It's a different concept. You could have 1 kilogram, for example, this weighs a lot, by the way, versus this one in here, and they almost have the same volume. They occupy the same space. So V is the same, and M is different. This one, if I put it on a scale, it's heavier, it weighs more than if I put this one on the same scale. Okay, if I put them on the scale, this one tips the scale. So that is this key concept in here. So instead of doing that, so the concept of inertia again involves mass. Okay. So there is a conversion factor, at least here on Earth. Every kilogram is 10 times as much, or at least is a tenth of its weight, okay? And that is because, can I write in here? Do I have something to write with? Is this a writing pen? Yes. Oh man, it's a typing thing. I don't want to sign my name. No. Sorry about that. I thought it's a just a typing thing. G is equal to 9.80 actually in this area, 0 something meter per second squared. So this is the quantity we use to convert a kilogram. We roughly, approximately, equals to 10 meter per second squared. So that is the value of G on Earth, okay? That is the value of G on Earth. So if you weigh 700 newtons, that is about 70 kilograms because you divide by 10. Okay. So the weight now depends on the force of gravity. But that's actually another way of measuring masses too, at least here on Earth, okay? But you have to be mindful of where you are to measure these masses. Here is an experiment that we could have conducted, but I tried and it couldn't get anything to work for me, so I'm gonna just describe what it is, okay? What you have in here, you have a heavy object, okay? Connected with the same string, or at least two strings of the same type, on one side, and it's hanging from the other side, and you pull it from the other side. There are two ways of doing this experiment. If you come in very slow on it, the string will snap on the top in here. Because what's going on in this case, you have two forces acting on this string. You have the weight of this mass and the hand itself. So if as you're pulling, the combination of these two forces will basically snap this one. So what this illustrates is the weight effect of this mass, okay? Whereas if you come in and go very fast, very quick, in this case, what happened, and there is not enough time for this one to add to this force to snap this one. As a matter of fact, this will resist the change in motion because it's stationary, it doesn't want to move. So if we apply very large acceleration in here, it's going to resist that, causing this part of the string to snap. So the first demonstration, when you go slow, is actually illustrates the concept of weight of this mass in here, of the ball in here, okay? Whereas if you go super fast, it illustrates the concept of inertia, okay? Because the inertia is a change in motion. Same thing if you have seen those magic shows or whatever, those shows on TV, actually on YouTube, probably you can see them, where a person, the waiter comes in and snaps the string from underneath the table, and all of the things on the table, you know, like the dining table, all of the plates and everything stay in place. That is an illustration actually of the concept of inertia. Whereas if you pull them slowly, then in this case, you give them time to accelerate and they will drag and fall, okay? Similar to that. So a property that is of a great importance is the density. The density is a property of the objects. Each object has its own density. Copper, as I was illustrating earlier, is denser than iron. Iron is about 7.8 kilograms per cubic centimeter, or 7,800, almost 8 tons per cubic meter. So think of a cubic meter as basically, if you open your arm, I cannot see my other arm. Okay. It's longer than this, so probably this much. This is maybe a meter, okay? It's about 2/3 of you when you're standing, roughly, okay? Because we measure about 1.5 to 1.8 meters, most people on average. So it's a little over 2/3 of who you are when you're standing, okay? So stand about 2/3 that way, that is a meter, okay? So think of that in 3D. Think of that going this way, and going that way, and going this way, okay? That is a cubic meter. If you have that much of iron, it weighs almost 8 tons. That's a lot, okay? If you have that much of water, though, it weighs only 1 ton. So water is more dense. Iron is more dense than water, okay? Aluminum is a lot less dense than iron, but it's still denser than water, okay? Aluminum is about 2.7, almost 3,000 kilograms per cubic meter. Air, though, this room, for example, the one I was demonstrating it right now, is only about 1.5 kilos, or a kilo and a third, actually, 1.23 or something like that, kilograms, slightly over 1 kilogram per cubic meter. So air is a lot less dense than water, okay? So that's the reference in here. If you think about it, the densest object that we can think of are neutron stars. Those are super, super dense, and they are of the order 10 to the power 15 or 10 to the power 18 kilograms per cubic meter. So that is the concept of density, okay? So the density of 1 kilogram of iron is less on the moon, the same on the moon, greater on the moon, or all of the above. It is the same everywhere. Doesn't matter where you are. Oh no, I lost that thing there. So the correct answer is B. The density is an intrinsic property of an object. We will do, I don't think this class will do an experiment, but at least we probably will play with it a little bit. If you find a density of a material that you don't know what it is, okay? And you go and look at the table, consult the table, compare that number to the table. That is probably what that object is. When we do the solar system, for example, we will look at the density of the Earth and compare it to the density of Mars, compare it to the density of Jupiter, compare it to the density of Saturn. And that tells us what these objects are made up of. What do we have on Earth that is different than Mars, that is different than Jupiter, that is different than Saturn? That is a key concept because it tells me a lot without even having to go to a place. Just if I can find its density, basically finding how big it is, its volume, and estimating its mass based on the interaction of that object with one of its moons. Then I have a mass, I have volume, divide the two, I have density. That density tells me a lot of what makes that object. For example, we know in the solar system, the densest object, can you guess what it is, roughly? Okay, there is the sun, of course, don't forget the sun. There is that big deal in the solar system. There is okay, let's exclude the sun, forget about it. Just mention the planets only, okay? And if you know some of the dwarf planets, that's fine, like Pluto and Ceres and all of the other ones. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune, plus Pluto if you like, and other objects, Makemake and all of the other things. Which one do you think is the densest among all of these things? Any guess would work. Jupiter is a gas giant, that's true. But is it denser than anything else? Jupiter is the biggest one, okay? All of the other planets combined cannot, including all of the other basically asteroids and all of the dwarf planets, they cannot come anywhere near Jupiter. It's still much bigger. And that includes Saturn, which is the next biggest giant stuff in there. So which one do you think is the densest? No, Pluto is not. Okay, that's a good guess though. Mercury is the second densest planet. Earth is the densest among all of the planets in the solar system. And the second one is actually Mercury, okay? Because Earth has, we'll talk about that in terms of its structure when we get into it later on. So that tells me a lot. The reason why Jupiter is not, albeit it's super, super more massive, much, much heavier than Earth if you put them next to one another, because its volume is huge. It's mainly a gas, okay? So that's really what it is. It has more gas than what we have matter on Earth. That's why it's denser. Saturn, as a matter of fact, which has more mass than the Earth, it's actually lighter than water. If you find an ocean big enough to contain Saturn, it's going to float. It's not going to sink, okay? So that's some of the things that tells you a lot in terms just of the density. So the density is an intrinsic property of an object, meaning it stays with it. Wherever that object goes, it goes with it. It's like your name tag. If you attach that to your name with your birthday and social security number and everything else, and you walk with it, think of the density as just another number for an object that walks with it. It has it and it's going around in town showing itself that here I am iron, 7.8 kilograms per cubic centimeter. Okay. So in this case, it's the same everywhere. Okay. So a force, as simple as illustration is the one I was pushing back earlier, back and forth, but that's a simplified version of what the force is. So it's a push and pull, okay? Sometimes force act at a distance, like magnets, for example. You have magnets like this one. What is another magnet? Man, this magnet is super strong. I really don't want to use this one instead. These are magnets. They're push and pull, but at a distance. Okay, they act at a distance. Right now they're repelling one another. If I put them this way, they attract one another. Okay, so a combination of all the forces. So that's the net force. So when you're studying an object, you would want to know the net force on it. Because if somebody's pulling one way and somebody is pulling on the other side, well, these two forces, they cancel one another and there is no net force on it. End of the story. If one of them is pulling with 10 Newton, the other one is pulling with 5 Newton, then the 10 Newton will win. But if both of them are pulling in the same direction, then in this case, the net force is going to be greater. Okay. So the net force in this case, I have a 5 and a 5, that's 10. I have a 5 and a 5 and they're opposite to one another. So they cancel one another, but I have a 10 and a 5. And the 10 wins by this much, by the net force, which is 5, the difference between the two, okay? An object is said to be in equilibrium if the net forces are 0 on it. Yeah, let me do this. This is the object I was demoing earlier. Okay, they are not moving. They're stationary. The reason why they are stationary, let me get out of this thing because they tend to move because of any inclination will move them. This one is being pulled toward the Earth by the force of gravity. Remember, the Earth is pulling on it. If I remove this and let go of it, what happened to it? Is it going to stay in its place? It's going to fall because of gravity. But now this object in here provides a force to keep it from falling. So the net forces, which is the combination of these two forces, the force of gravity and the support force coming from this surface, cancel one another. The object stays in its place. So this one is said to be in equilibrium. It's not going anywhere. You guys understand? So that is actually the support force that we're talking about. The reason why you're sitting and not because the Earth is pulling on you is because wherever you're sitting, you're being provided a support force from falling. Okay, so that's really why you can sit still and why I'm sitting still in here. And the only reason why my hand and everything else is moving because I'm choosing other forces in here at play. But the point being in here, I'm not falling to the ground because I have a chair I'm sitting on it, and probably you too. So that's really the idea in here with the when you are an engineer, an architect to be more specific, you would want this to be true. When you build a building, you don't want it to collapse the next time a wind blows or a breeze or anything like that, okay? You want the net forces to be on its 0. That's why you have beams and you have supports and you have all kinds of things in it, in the structure, okay? To keep it from falling. So this is a big deal if you are an architect. You deal with this expression a lot. So again, what you need to know is that the force is a vector quantity. So when you're adding stuff, you make sure that they have direction and magnitude in here. Again, I mentioned the dynamic equilibrium, and that is at constant velocity. And I made an illustration, or at least I mentioned a few times in there. And that is if you're sitting in a car cruising at constant speed, then in this case, you could say that you are at equilibrium because the cup of water is not going anywhere, okay? At least the tip of it. So that's an equilibrium, but that's a dynamic equilibrium, equilibrium and motion. That means the velocity is not changing. So what matters really And the equilibrium is not that you're not moving. It's not that V is equal to 0. V is not changing. That's really what matters. Let me ask you a question. Are we really sitting right now? Are we really in stationary? Are we all not moving at all? What do you guys think? Right now, am I moving or not? Or you, for that matter? I don't understand. Is it yes for moving or yes for not moving? Okay, can you illustrate? Can you tell me why? Both of you are right, but can you tell me why? Because right now it seems to me like I'm sitting, and you are too. Okay, the motion of the Earth. We are sitting on a big ship that is moving. Actually, the Earth is spinning, and the Earth is actually going around its axis. And we have moved so much, at least from when we started at 9 o'clock until 10 o'clock in 1 hour. We've covered hundreds of miles, literally speaking. So we were not where we started from. When we started from, we were way back. And by the time we end this class, we're going to be so much far in the ahead. So that is actually the idea too. So we're not really in a static equilibrium. We are in a dynamic equilibrium. So this idea here is that in equilibrium, the key idea behind it is that V is equal to constant, not necessarily 0. Okay, 0 is just a special case of it. Okay, that is static equilibrium. This is what we mean by dynamic equilibrium. As long as V, and V actually has to be a vector. V as a vector, not V as a speed. Okay, that is what we mean by equilibrium. Meaning keep the magnitude and keep the direction in the same place. That is equilibrium. Okay. We have quite a few slides, so I'm going to skip through these questions. Hopefully you guys can, if you have any questions about them, please do not hesitate to ask, which is you're very much encouraged. Please do not think that, okay, the reason why I did not understand that is because probably you did not think about it hard enough. No, that's not correct. When something is not clear to you, please ask it, and you will be surprised how much, first of all, probably I did not explain it correctly, or how many other people also would want to ask that question, but they probably did not think about it at all. So please do not hesitate to ask at all. So go through these things and do ask them. Again, I mentioned the support force already. I gave an example for it. Okay. This is sometimes you will find that in the literature mentioned the normal force. Okay. So you see that word a lot. So when you're reading or when you're doing some of the homework assignments and things like that, it is called the normal force because it's always perpendicular to the surface. Okay, it's always perpendicular to the surface or the contact point. Okay, so that's why it's called the normal. So when you push on spring, the spring push back again in this case. That is actually spring force in here, which is a different force in here, but this one is. The spring itself is under a normal force now because of the contact with the surface. The key word for a support force is surface. Okay. So again, when you stand on scales in here, what you're reading is actually the scale support force. So that's actually what you read. So your weight, I know we call it the attraction of the earth or how much the earth is pulling on you and things like that. But actually what is being read is actually the support force. That's all you're reading. As a matter of fact, you can do the following, okay? You can go on an elevator and you will be weightless. All you have to do is, or probably have experienced that one, when the elevator is coming down, do you feel you weigh less or not? Do you feel like, do you have that sensation when you are on the 7th floor and the elevator starts to go down, you feel that you're weighing less, okay? But when it comes down to slowing down or stopping at the end, the first floor, you feel actually you're heavier, yes? That is actually what's going on in this case, because as the elevator is accelerating down, in this case, you're pushing less on the floor of the elevator, which means it's pushing less on you. And actually, if you stand on a scale, you will read less weight. And as the elevator is slowing down to stop on the first floor, you're going to feel heavier. As a matter of fact, if you're standing on a scale, the scale will tip heavier, will show more weight. That is exactly what's going on. So we are in February. People are crazy nowadays about losing weight. So there is a plan for you, okay, business plan. All you have to do is build an elevator, put people on it who want to lose weight, collect the money up front, okay, before they go on, okay? Okay, and then once they are on the 7th floor, cut the strings of the elevator. They will be completely weightless. Okay? Don't mention me in the lawsuit afterwards, okay? But make sure you collect the money up front. So again, what you're reading again is the normal force or the support force. In this example, you're standing on 2 of them, so half of the weight is going to be here and the other half is going to be there, okay? If the weight is distributed uniformly on 2 sides. Again, I mentioned the force of friction. That was one of the things that we started with. And this force of friction is always between 2 objects, okay? The air in your hand, the hand in hand, and this is a dissipative force, that wastes energy, okay? We'll talk about it later on, okay? So a resistive force that opposes the motion, it always against the velocity though. It does not oppose the change in motion. It's not an inertia. This opposes the actual motion itself. If an object is moving this way, the friction is in the opposite direction. That's it, okay? There are 2 kinds of friction, at least 2 kinds. There are more than 2. There is a so-called static friction. If I want to move this desk right now, it's not moving. So this is a static friction. But if the desk starts moving, I need to maintain it at constant velocity. That is dynamic equilibrium. That means actually this is a dynamic friction. Kinetic friction, it's called. And then there is the example I mentioned earlier. When somebody falls in the air, there is another friction in this case, and that is the drag from the air. Okay? And that's what parachutes use in order to slow down. Okay? There is another friction, and that is from liquids, and that is actually called viscosity. So friction is everywhere. Okay? Friction is everywhere, whether in liquids, gases, or solids. Again, microscopically, what's going on is the grooves in the atoms and the electrons of the 2 different objects interacting with one another via electricity, electrical forces, something that we will discover later on. So when Nelly pushes a crate, a factory floor at constant speed, the net friction between the crate and the floor is equal to whatever she pushes with. Because this one is going at constant velocity. Remember, when V is constant, because this is uniform, constant speed. So V is constant. When V is constant and she's pushing, the friction must be pushing back so that the sum of the forces is equal to 0. So if she's pushing with 10 Newton, the friction is pushing back with 10 Newton. Okay? That is basically what this expression is saying in here. This is a kinetic friction. And like if you push on something and that something is not moving, so of course they have to be opposite to one another for this one to be true, okay? Now, if she accelerates it, then of course she has to apply more force, okay? Than the friction. If the object is not moving, there is still friction. Let's go back into the first illustration here. If the object were not moving at constant speed, meaning that V is equal to 0, and she's pushing with 10 Newton, if there was no friction, this object need to move at all. It should move. It cannot be stationary. But because there is friction, then it will keep it from moving. You guys understand that? As long as V is equal to 0. So in either case, there is friction, whether in the case of static or in the case of dynamic, as long as she's pushing. If she stops from pushing, there is no friction. So the fact that the desk right now is sitting by itself and I'm not pushing on it, that is actually no friction. But the minute I start pushing, there is friction because it's not moving. This is static friction. If it starts moving, it's still friction, but that's a kinetic friction, 2 types of friction in here. This is the concept we've been talking about, and that is the concept of speed. The speed is actually distance covered per time. The unit for it, and it's a big deal, okay, please remember the units, is a meter per second. How many meters are you going to cover for each second? That is in the system. So far we discovered the kilogram, and we discovered the mass, that is in kilogram. We talk, the mass is in actually, the distance is in meters, and the time is in seconds. So these are the units we have discovered. Kilogram for mass. We discovered meter for distance, and second for time. So those are 3 of the 4 important units. The 4th one, which we'll be talking about it later on, is the A, which stands for ampere. That's the French physicist who basically discovered these things, for the current. Once we have that, we have covered everything in the SI system, the Système International, which is the system of measuring things, okay? This is SI, which is le système. Okay, I'm gonna write it without accent, international. It's a French word now, it's used, SI, International System of Units, okay? So, these are the units. So far, we discovered these 3. The 3rd one, the 4th one, we'll be talking about it later on down the road when we do electricity and magnetism and things like that. So again, this is the distance, which is like miles per hour. That's actually speed, 50 miles. So we're not using meters instead, we're using miles. And there is a set number of meters per mile, and then per hour, and there is a certain number of seconds per hour, okay? There is a certain number of minutes per hour and a certain number of seconds per minute. So it gives you a total of 3,600 seconds. For the miles, there is 1.609, I think, kilometers in a mile. And there is 1,000 meters per kilometer. So there is 1,609 meters per mile. So if somebody is doing 50 miles per hour, I can do the algebra quickly here. 50 miles, well, miles is actually, I know what it is. It's my 1,609 meters per hour, and 1 hour is 3,600. So I can pull my calculator quickly, and do I have it open? No, it's not. So what is it? 50, I'm doing 50 miles per hour, okay? 1,609 divided by 3,600, 22 meters per hour, meters per second, I'm sorry, 22 meters per second. 22 meters per second. Now you know. 50 miles per hour is 22 meters per second. Okay, it's a good idea to have an estimate of things, but this is an SI now. It's the same thing. The fact that you're cruising at 50 miles per hour is the same thing as 22 meters per second. It's the same, but now this is in this system, which is the standard system used by scientists, whereas in everyday talk, we use miles per hour in here. We say 50 miles per hour. I know that there are this many meters per mile here. And I know that there are this many seconds per hour. So that's why this conversion works for me. And that's how basically I have this thing in here, 22 meters per second. This is not an algebra-based course, so you're not expected to do heavy stuff in here. except simple stuff in there. So if you have difficulty with it, please let me know, okay? So you're not expected to do all of this math in there, okay? So, but just to give you a sense of things, when I first came to this country way back, a long time, way before you were born, probably most of you, and the weatherman was talking, temperature tomorrow is going to be 70 degrees and it's going to be beautiful. I was alarmed because I have no idea what 70 Fahrenheit is, 70 degrees is. So I have to really use a calculator to know that, oh, that's a comparable temperature, you're right, okay? Because I was used to the Celsius and I was used also to the meter per hour, kilometer per hour and things like that. Until now, in my head, honestly, for the temperature, still I have to do conversion to really feel, to have the proper attire and the proper feel for what that temperature means, okay? So again, numbers talk and they tell you things. They actually speak to you. So if somebody calculates and finds a speed, let's say, for example, doing a math, and they found the speed of the train is 17 meters per second. Well, that's a crazy train. That's probably floating. That's going super fast. Okay. It's going to be what, 400 miles per hour, something like that? That's crazy, okay? So if an officer tomorrow, there is a speed limit, for example, of 35 miles per hour, and you're cruising at 55 or 50 miles per hour in downtown, I don't know, Corona, for example, okay? And he stops you for speeding, going 15 miles over the speed limit. What are you saying, officer? He says that you're doing 50 miles per hour. No, I'm doing just 22. Here is defense. Don't tell them the unit though, okay? And don't mention my name because probably you would be in trouble already, okay? Okay, so again, the average speed is different than the instantaneous speed. What you look in when you look at the odometer in your car is the instantaneous speed, the speed at that moment, okay? But you could be moving and slowing and stopping and moving back and things like that. So if you go from home to work and come back home, your average speed is 0 because the total distance is 0 in this case, albeit you spend 8 hours at work. So 0 divided by 8 is still 0, okay? So that's a concept of an average speed. So the instantaneous speed is when you look at your odometer, okay, versus the average speed, which is the total distance. So if you happen to go in a circle and come back, then your average speed is 0, okay? But if you do this measurement very, very close from one another, then the average speed will be equal to the instantaneous speed, okay? Okay, this is the question that we had earlier about the fact that we are on Earth and the Earth is moving 30,000 kilometers per hour. Wow. At the same time, your speed relative to the sun is about 100,000 kilometers per hour. So in an hour, since we've been talking, no more than an hour, we traveled more than 100,000 kilometers. Isn't that amazing? We've been on the same trip altogether. Okay. The acceleration is the rate at which the speed is changing with time, or the velocity is changing with time. So the units for the acceleration, again, are going to be, so the acceleration, the symbol for it is A. So the units are how many meters per second change per second? So it's a meter per second per second. So for example, if you hear the commercial, this car can do 0 to 60 in 5 seconds. That is an acceleration, actually. It changes from 0 speed to 60 miles per hour in 5 seconds. So it does 60 miles per hour divided by 5, which is 12 miles per hour per second, okay? Albeit the time now is not the same thing. You can use the earlier math to find out how many per second per second. Sometimes we write this one instead as meter per second squared, that's all, okay? So that's the same thing. So when you see a unit meter per second squared, that means it's a meter per second, okay? That's what I used earlier for G, for the value of the gravity. So again, the acceleration is the rate of change of the velocity. So it's the rate of the rate. Remember, the velocity is the rate of change of position. This one is the rate of the change in velocity. Okay. The last topic in here is the free fall. The free fall is when the only force acting on object is the force of gravity. Again, I gave the value in there earlier. G is equal to 10 meter. This is an approximate value. This is not an exact value. The exact value is 9.8. So every second, you gain 10 meters per second. So if the object starts as stationary, the next time it's going to be moving faster by 10 meters per second. The second after that is going to be even moving faster than the previous second by 10 meters per second. And the third second is going to be traveling faster by another 10 meters per second. So it's going to be moving faster and faster as it's moving. So it's going to cover more and more distances because the speed is the rate at which distance is being covered. That's why you see the ball in here, or this marble being dropped in here. So this distance is less than this distance, which is less than this distance, which is less than the next distance, and so on and so forth. So this is what we mean by the free fall. The acceleration is constant. The formula for the distance is the distance is 1/2 times this value of G times the square of the time. Times the time squared. So this is basically the formula on how to find the distances, okay? Again, you really don't need to know the exact how this thing's in there, but it's a good idea to have an understanding of what that means. This distance is a lot less than this distance as you move along. Because it's accelerated. It's gaining more and more speed as it's moving, okay? I'm going to leave the rest of the questions for you guys to cover it. This is the table explaining exactly what I was talking about. Time of flow, 0 second, velocity 0, the distance traveled is 0. After 1 second, now it was 0, the speed will add 10 meters per second to the previous speed. But the distance now is only 5 because 1/2 times 1 squared is 5. Covered 5 meters only. The next time around, 2 seconds. So it's going to be 10 plus 10, which is 20, because every second you add 10. So between this and this, add 10. 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 But the distance, man, you have to do a little bit more work to find it, okay? You have to multiply 1/2 by 10, which is 5, times the time squared, and the time squared is 2. 2 squared is 4. 4 times 10 divided by 2, that is actually 20. And the same is true for all of this math in there. So if in doubt, go back to the same thing as I said before. So the distance, am I typing? What happened in here to all of this typing? The distance for some reason, it's not that typing for me. Well, the distance is equal to, okay, it's this expression. 1/2 times G. G, we're taking it to be 10, okay? Approximately 10 meters per second squared. Okay, so let's say 4, for example, okay? Let's do this one. Let's see, this one is equal to 80. Let's see, the distance is equal to 1/2 times G. G is 10 times 4 squared. 4 squared. Well, I know that 1/2 times 10, that's 5, times 4 squared, that's 16. 16 times 5 is 80. If you don't trust me, pull a calculator. You should find it 80. You should find this number. Okay? Yes? Again, you really don't need to know the details of how this thing in there, but it's a good idea to have an understanding of where this thing is coming from. Okay? That the distances, they change in there at this ratio. Okay? So This is the last slide. Let me stop sharing in here. Remember, today I made it light in purpose. I know it's not light stuff. I know this stuff probably if you have never had it before, it kind of sounds like kind of a little bit hard. But in terms of the discussion, there was only one item, and I'm coming back to it in here. I'm hoping that you guys picked it up on it, and you're going to answer it toward the end. And that's the end of this class in here. I have another class that's going to start in about 5 minutes. Do you have any questions? No? Okay. I see you guys next week. I mean, next week, Thursday. Bye.
Bye.